Chapter 17 is on expected value and standard error. Continue. Now we're going to talk about the normal curve. So for a large number of draws, the sum of the draws will follow the normal curve with an average of the expected value of the sum and standard deviation SC for the sum. Now here's the part that we like the normal curve for. So 68% of the time, the sum of the draws will be within the expected value plus or minus SC of the sum. So remember how we said we expect our winnings to be about this much, give or take so much? That's what we are doing right here with this expected value plus or minus this SE. And we said those were our likely numbers. So that's 68% of the time the sum will be within those two numbers. If you want to be even more sure that you have the right range, 95% of the time your sum will be within the expected value plus or minus 2 standard errors. And we can actually use the normal curve to find the chance that the sum of the draws is in any region of interest. What you have to do is because to use the standard, or to use the normal curve, you always have to standardize. So we're going to use the expected value of the sum and the standard error of the sum to get standard units. So it's going to be Z equals the sum minus the expected value of the sum over standard error of the sum. If you remember back in chapter 5, it was X minus the average over the standard deviation. But those were just for individual numbers. Now we're dealing with sums, so instead we're going to do sum minus expected value of the sum divided by standard error of the sum. Okay, now there are a few important notes for using the normal curve for the sums. First is that it doesn't matter what's in the box, and the histogram for the tickets in the box don't have to follow the normal curve, because the sum of the draws will follow the normal curve even if the tickets in the box are just ones and zeros. And in fact, you don't even need to know what's in the box, you just need to know the average and standard deviation in the box. But to use the normal curve, you do need to have a large number of draws. Our rule of thumb is that you should have at least 25 or 30 draws. So at least 25 or 30. So once again, in order to use the normal curve, you have to have a large number of draws. Okay, so for this next example, we want to roll a die 100 times and count the total number of spots. What is the chance that the total number of spots is more than 367? And from example 173, we know that the expected value of the sum is 350 and the standard error of the sum is 17.1. So we don't have to do the expected value and standard error again. We can just skip straight to what is the chance. So because we're using a chance, we're looking for a chance, we're going to use the normal curve. Now we're rolling a die 100 times, so that's 100 draws. That's a large number of draws. So we can use the normal curve. So Z is equal to the sum of interest minus the expected value of the sum divided by the standard error of the sum. So the sum that we're interested in, is this 367. Minus the expected value of the sum is 350, and the standard error of the sum is 17.1. So this gives me 0.994. So I found my Z. Now remember back to chapter 5, what do we do after we know our Z? We draw a picture. So Z is 0.994. And we're looking for the chance that the total number of spots is more than 367. So that sounds like we should be looking for the area to the right. So area to the right of, now let's go to our standard normal table. And we're looking for Z equals 0.994. Notice 0.994 isn't on here, but Z equals 1 is on there. So let's use that Z equals 1. So we're looking for the area to the right. To the right of Z equals 1. So we round it up to 1.00 so we can use the table. Now keep in mind though, the table only gives us areas to the left. So this area of 84.13, that's the area to the left. So how are we going to find the area to the right? We're going to have to use the complement rule. So 100% minus 84.13% gives us 15.87%. So the area to the right is this 15.87%. So that's my final answer. What does this actually mean? So, if we roll a die 100 times, we expect to get the sum, or 350, to get about 350 spots, give or take 17.1 spots. So that's kind of what we already knew from the previous video. Okay, and now we can go into even more depth. The chance of getting 367 or more spots is 15.87%. So that's what we just barely learned how to do, is to add in that information. So let's try our next one, example 176. A multiple choice test has 20 questions, each with 4 choices. Each correct answer scores 5 points. Each wrong answer makes you lose 2 points. The student guesses all the answers. From example 175, the expected sum is -5 and the standard error is 13.5. He needs 20 points to pass the test. What is the chance that he passes the test? Let's just make ourselves a note here. So based on the previous information, he can expect to get about -5 points, give or take 13.5 points. So that's what we know previously. Now we're going to go into even more depth and say, what's the chance that he passes the test by getting 20 points? So to find a chance, you do the sum that you're interested in minus the expected value of the sum divided by the standard error of the sum. So the sum we're interested in is 20 points. He needs 20 points to pass. So 20 minus the expected value of the sum, which is -5, divided by the standard error of the sum, which is 13.5. So this gives me 1.845. And then we need to draw a nice little picture. So here's my z equals 1.845. We're looking for the area to the right of that. So the area to the right, and I'm doing it to the right because he needs 20 or more points, to the right of z equals 1.845. We come to our normal table, we look for 1.845, the closest is this 1.85, and the area to the left is 96.78. So if we do 100% minus 96.78%, we get 3.22%. So he has a 3.22% chance of getting 20 or more points to pass the test. And that's how you use the normal curve. Now we're going to talk just briefly about sampling without replacement. So for sampling without replacement, everything with the box models we've been doing was based on the premise that we were doing sampling with replacement, so that the probabilities weren't changing with each draw. But it turns out that sampling without replacement, as long as it comes from a large population, is just like sampling with replacement. Because if our original population is much bigger than our sample, then it doesn't matter if we sample without replacement. Technically, our probabilities do change a little bit with each person, but the changes are going to be so minuscule that they don't really affect our answer. So to make the problem actually doable, we pretend that we're sampling with replacement for the actual calculations. Now again, this only works if we're coming from a very large population where there's so many people that it doesn't really matter if you've taken one out already. Let's see, a large crop of apples has an average weight of 4.3 ounces with a standard deviation of 1.5 ounces. I choose 100 apples at random. What is the chance that the total weight is less than 25 pounds? So there's a few things to note here. So we're looking for the chance that the sum of 100 draws is less than 25 pounds, but we're dealing with ounces already, so let's change that to pounds. It turns out that all you have to do is times it by 16 because there's 16 ounces in a pound, so 25 times 16 is 400 ounces. So we just changed pounds to ounces. So what is the chance that the sum of 100 draws is less than 400 ounces? Now, it doesn't actually talk about a box. This is something that's a little bit new to us. So if we know the information about the population kind of tells us the information in the box. So the population tells us that the average of the box is 4.3, and the standard deviation of the box is 1.5. So again, the population, that's what you're drawing from. You draw your sample from a population. So we know the average of the box, standard deviation of the box. We need to find the expected value and the standard error. So the expected value of the sum is equal to the number of draws times the average of the box. So this is going to be 100 times 4.3, which is 430. And the standard error of the sum is equal to the square root of the number of draws times the standard deviation of the box. So it's the square root of 100 times the standard deviation of 1.5, which gives me 15. So we found the expected value and standard error. Now we're looking for the chance, and anytime you're looking for a chance, and as long as you have a large number of draws, we're going to use the normal curve. Now let's standardize and find our z. So sum minus the expected value of the sum, divide by the standard error of the sum. The sum that we're interested in is that 400 ounces, so 400 minus our expected value, 430, divided by the standard error of 15. So this gives me -2. So we're looking for the probability that z is less than -2, or the area to the left of -2. So go to your normal table, -2, the area to the left is 2.28. So 2.28%. So that's our answer. What does this mean? So there is a 2.28% chance that the total weight of 100 apples is less than 400 ounces, or 25 pounds. Example 178, suppose 10% of people in a large population are underweight. If we take a random sample of 1,000 people from this population, what is the chance that more than 103 of them are going to be underweight? Notice this, the chance that more than 103 people, to me this sounds like we're counting the number of people. Whenever you're counting something, the numbers in your boxes are just going to be ones and zeros. And you'll notice that I didn't tell you what the average and standard deviation of the box or the population is. So we're going to have to calculate that by hand. So let's actually start off with designing our box model. So we're taking a random sample of 1,000 people, so it's going to be the sum of 1,000 draws from the box and what goes in the box. Now this is where it's a little bit different. We haven't done anything exactly like this. So we're counting the number of people that are underweight. So we'll do a 1 for underweight, a 0 for not. So the 1 is underweight and 0 is for not. And we don't actually know how many people are in the population. So we can't say there are 15,370,000 people that are underweight or something like that. Instead, we just know that 10% of the people in the large population are underweight. So if there's 10% that are underweight, we could just say, what if we just do 10 tickets? And for the not underweight, we could do 90 tickets. It turns out that we don't actually care necessarily how many people are in the box as long as we have the right ratio. And 10 to 90 does give us that correct 10% ratio. So now that we've done that, let's find the average of the box. The average of your box, well, we're going to have to do 1 plus 1 plus 1 plus 1 plus 1 10 times, and 0 plus 0 plus 0 plus 0 90 times. Or for shortcut, I could do 10 times 1 plus 90 times 0. So really, I'm adding up those 100 tickets one by one. I just don't actually want to write it out. And then divide by how many there are, because there's 100 of them. So that gives me 0.1. And the standard deviation of the box, we're going to use that shortcut formula. So big number minus small number times the square root of the fraction with the big number times the fraction with the small number. So the big number is 1, small number is 0. The square root fraction with the big number, there's 10 out of 100. And fraction of the small number, there's 90 out of 100. So this gives me 0.3. Now for the expected value of the sum, that's the number of draws times the average of the box. So there are 1,000 draws. The average of the box is 0.1, so this gives me 100. The standard error for the sum equals the square root of the number of draws times the standard deviation of the box, so 1,000, the square root of 1,000, times the standard deviation of 0.3, gives me 9.48. So we expect about 100 underweight people, plus or minus 9.48. So at this point, we can stop, we can take a break and say we expect 100 or about 100 underweight people, plus or minus 9.48 people. Now, what is the chance that more than 103 people are underweight? So we said we expect about 100. What's the chance that it's more than 103? So now to find the chance, we have to use the normal curve. To use the normal curve, you need to know what z is. So z is your sum minus the expected value of the sum divided by the standard error of the sum. The sum we're interested in is 103. Expected value is 100. Standard error is 9.48. So this gives me 0.3164. So here's my z equals 0.3164. We're looking for more than 103 people, so we'll shade to the right. We go to our normal table. We look up 0.3164, or 0.3 is probably our closest, so the area to the left is 61.79. So 100% minus 61.79% gives me 38.21%. So that's my final answer. So what is the chance that more than 103 of them are underweight? 38.21%. So there's our 38.21% chance that 103 or more are underweight. So we expected about 100 underweight people, plus or minus 9.48. If you're interested in specifically more than 103 people being underweight, then you have a 38% chance. And just one more. For Haines women, 19 to 24, a histogram amount of beef eaten over a 3-day period has an average of 22 grams and a standard deviation of 41 grams. Okay, so again, this is kind of our population, which represents our box. So the average of the box is 22, and the standard deviation of the box is 41. Suppose I choose 200 of these women at random and look at the total amount of beef eaten. What's the chance that this total exceeds 5,000 grams? Okay, so we're interested in the sum of 200 draws. And we're looking for the chance that the sum is greater than 5,000. Now 200 draws is a lot, so we can use the normal curve. First we need to find the expected value and standard error for the sum. So expected value of the sum is the number of draws of 200 times our average of 22, which gives me 4,400. The standard error of the sum is equal to the square root of the number of draws times the standard deviation of the box. So 579.8. Now to find the chance, we calculate z, so z is equal to the sum minus the expected value of the sum divided by the standard error of the sum. So the sum we're interested in is 5,000 minus our expected value of 4,400 divided by our standard error of 579.8. This gives 1.03. So when I draw my graph, I'm looking for the area to the right of z equals 1.03 because we're looking for the chance of the sum is 5,000 or greater. So if we go to our normal table, we have our 1.03, 1.034. So this 1.05 is the closest. So there's 85.3% to the left. So I'm going to have to use the complement rule to find the area to the right. So this will be 100 minus 85.31. Which gives me 14.69. So there is a 14.69% chance that the total amount of beef eaten exceeds 5,000 grams. And for our final question, does it matter that the histogram is not like the normal curve? And why or why not? So, no, it doesn't matter, because 200 draws is a lot, so we can use the normal curve no matter what the original histogram looked like.